central metal atom, you have the electrons jumping and pairing up. But this, because it makes the electrons, it gives energy because of its repelling power. It causes it to the electrons to pair up. So the pairing energy is relatively less as compared to the them staying separate. So they pair up, and now this prefers forming a more stable complex, which is termed as an inner orbital complex, giving a D2sp3 hybridization. So this is a D2sp3 hybridization, and this happens. There are a number of factors normally that come into play. It could be the nature of the central metal atom, it could be the nature of the ligand that are approaching. Some are known as weak ligands, some are known as strong ligands. Why they are weak or strong? At that time, Linus Pauling could not explain that, but we were able to, based upon there, because one was found to be paramagnetic. So the explanation that he gave, that the hybridization takes place with the outer orbital, with the 4d orbitals. That is why an outer orbital complex is formed, and that explains the paramagnetism in this complex. In the halide, mostly the halides and tend to give you, they are taken as the weaker ligands, and they give you paramagnetic character, and they give you the outer orbital complexes, as compared to ammonia, CO, the carbon monoxide, the complexes which are the carbonyl complexes as we call them, the amine complexes. They are stronger ligands, and they tend to cause pairing, leading to a relatively more stable complex, giving you D2sp3. That is, the 3d orbitals are coming in picture here, and the 4s and 4p. So 3d, 4s, 4p, they hybridize together, they mix up together to give you 6 equivalent orbitals, giving you what is termed as inner orbital complex. So these are examples of octahedral complexes. Coming to examples of the 4 coordinates complexes. Now you have, normally you'll find that the complexes of palladium in +2 oxidation state, platinum in +2 oxidation state, nickel in +2 oxidation state, nickel, palladium, platinum. In +2, they are usually 4 coordinate, square planar, and diamagnetic. 4 coordinated, square planar, and diamagnetic. This is in general you'll find for nickel, palladium, and platinum in their +2 oxidation state. Here normally what happens in most of them, what will be the ground state electronic configuration? It will be D8. So you can have 3D8, 4D8, or 5D8, depending upon whether you're talking a nickel, palladium, or platinum. And normally here you'll have the say example. What example is here? Let us take the example here. Now this is again chromium. Chromium. Let's come to some examples of. So in chromium also you'll see in iron 2, again we saw iron in +3 state and iron in +2 oxidation state, depending upon whether what sort of a complex is formed, whether it is paramagnetic or diamagnetic. So if it is paramagnetic, that means it has to be a complex will be formed such that you will have, say, in this one. Now in iron in FeCN6 4-, we saw that iron is in +2 oxidation state here. So in +2 oxidation state, what is going to happen here? Here you will have cyanide being a stronger ligand. It causes it to pair up. So that means this was the diamagnetic complex. So by experimental value, you found that this is diamagnetic. So you have D2sp3 hybridization taking place, and since it is a 3d orbital involved, so you say that the hybridization is an inner orbital sphere complex. Inner orbital or inner sphere complex is formed, and it is diamagnetic, so it is D2sp3. Now let's take another example here, FeCN6 3-. This was FeCN6 4-. Here in FeCN6 4-, what do we see? This is iron in zero oxidation state, iron in plus 3. Here, the iron is in plus 3 state in ferric state. So plus 3 oxidation state. So here, this is plus 3 means 1, 3 of these go off. So 1, 2, and the third one, of course, the one which is paired up is the one to go off. So iron in plus 3 state has 3d5. In this, you have one electron in each of the 5d orbitals. And when cyanide being a strong ligand, we know that pairing can take place. It will push the electron to pair up. So these two pair up, and we get an hybridization of D2sp3 itself. But there is one electron here, and it is paramagnetic in nature, because despite the other two pairing up, because here iron is in plus 3 oxidation state, that means that it was able to give you one electron here, one extra remains, and you have D2sp3 hybridization plus paramagnetic. So FeCN whole 6, 3 minus, would be a paramagnetic and an inner orbital complex, whereas FeCN6, 4 minus, would be diamagnetic, because you do not have any unpaired electrons. So with the help of these simple box diagrams, one valency bond theory is able to explain the paramagnetism and diamagnetism based upon hybridization, the type of hybridization that is taking place, and the ligand that is there, the weak ligand or strong ligand experimentally as they are done. So you tend to find that the halides are normally weak ligand, cyanides and ammonia, they are carbonyls, they are stronger ligands. Now coming to the 4 coordinate complexes, you have nickel. Nickel here, you have a nickel in zero oxidation state. You have 2 to 4 to 6 to 8, 3d8, 4s2 is nickel. Nickel in plus 2, here there are 4 of chloride, so 4 minus. So nickel X, that is X is equal to this minus 4 will go here, plus 4, so plus 2 oxidation state. So nickel here is in plus 2 oxidation state. So you have these will remain, 3d8 remains here, and you have chloride ions. So and this was paramagnetic in nature, and halide we have seen. So we find that the halides are relatively weaker. They do not have enough power to cause the pairing to take place. So it remains, it does not pair up, and it gives you a tetrahedral complex. Otherwise, if it was a stronger ligand, then what would happen? Then this strong ligand, like a CN ligand, if it is there, then it can cause the pairing to take place, and this will pair up here, and you would have DSP2 hybridization. So in the 4 coordinated ligands, you can have either tetrahedral, that is sp3, or you can have DSP2, that is square planar. So 2 types of structures are possible, either square planar or tetrahedral. So if the ligand is weak, then it just takes up the 4s and 4p and forms sp3 hybridization to give you 4 equivalent orbitals, in which the chloride lone pair of electrons are shared with the central metal atom, and these two remain as lone pairs, thereby making this complex as paramagnetic. So the paramagnetic behavior was confirmed experimentally. So one could say that yes, it is sp3 hybridization. Shape is tetrahedral in nature, and it is paramagnetic. Now take an example with CO. CO, as we see, they are stronger ligands, and nickel in this tetracarbonyl nickel compound, it is. This is a neutral molecule, because CO is neutral. The ligand here is neutral, so that means nickel here is in zero oxidation state. So nickel in zero oxidation state means 3d8, 4s2. So allowing the complex, it remains as 3d8, 4s2. So now what is going to happen here? Nickel will be, the 4 of these are going to occupy this, because carbon CO is a strong ligand. What is going to happen? These 2 electrons that are present in 4s are going to pair up, jump and pair up, spend some energy and pair up with these 2 Thereby, this becomes completely filled, and the hybridization now takes place with 4s and 4p to give you four equivalent orbitals in which the electrons are shared. The lone pair of electrons of the carbonyl are shared with the central metal atom, so thereby giving you an sp3 hybridization. So sp3 meaning tetrahedral structure, and a pairing has taken place, so there are no unpaired electrons here, so that means it is diamagnetic in nature. So nickel in this compound, in this complex, it is sp3 hybridized, it is tetrahedral structure, and it is diamagnetic in nature. Whereas nickel with the halide, in this it was nickel here was in +2 oxidation state, so these two electrons had been removed out, and nickel gave you sp3, but here they had lone these single unpaired electrons were there, so this is paramagnetic. Hybridization is sp3, so the shape is tetrahedral. So tetrahedral structure, paramagnetic, and hybridization sp3 with the halide. With the carbonyl, it was sp3 tetrahedral but diamagnetic. Now let's take another example, nickel cyanide. Nickel cyanide here, unlike the carbonyl here was neutral. Cyanide is negatively charged. So we have a charge on nickel here. Nickel is the overall charge on this ion complex is -2. So nickel here is +2 oxidation state. +2 oxidation state means no, this two orbital electrons have been removed out. So we have, this is the a box diagram that we'll show for nickel in +2 oxidation state. When cyanide approaches the ligand, as the cyanide as ligand approaches the nickel in +2 oxidation state, cyanide being a strong ligand, it causes this electron to pair up and thereby makes available this dsp2 hybridization. So a dsp2 hybridization takes place and the shape is square planar. The shape that we get for dsp2 is square planar. So a square planar shape with dsp2 hybridization. And advantage here is that because cyanide was a stronger ligand, it could get at a lower energy level. You could use up the 3D instead of using all the 4p going to a higher orbital. It got the advantage because of it being a stronger ligand. It tends to pair up these two electrons, so they get paired up. So that much energy it is ready to spend because it is getting a vacant 3D orbital, which is at a lower level. So it forms a stabler complex here, giving you, so with the help of spending a little bit more energy to pair up, it is able to make one orbital vacant for itself in the 3D and thereby lead to a greater stability by having a hybridization of dsp2, which gives you a square planar structure. So you can explain why this this complex of nickel with cyanide gives you a square planar structure, or why is this diamagnetic, whereas this complex of nickel with the carbonyl is diamagnetic but tetrahedral. Nickel, this is diamagnetic but tetrahedral because of these being nickel being here in zero oxidation state, because this is an electrically neutral molecule. Carbonyl is carbon monoxide is neutral. So this is electrically neutral. Hence you had all the 10 being adjusted in this, and this had the S and P available. So it gave you an sp3 hybridization because of the electrons getting paired up, because this is also a strong ligand. So it could cause the electrons that were present in this to pair up here and give you sp3 hybridization. So nickel with carbon monoxide with the carbonyl ligand gives you an sp3 hybridization and diamagnetic, but nickel with cyanide, because this is an iron, nickel here is in +2 oxidation state, here nickel was in 0 oxidation state. So in zero oxidation state, nickel with in this complex gives you sp3 and diamagnetic, whereas nickel in +2 oxidation state gives you a dsp2, that is square planar structure, but yet it is diamagnetic. So the resulting complex is diamagnetic. So we saw complexes of nickel with chloride, which was simple. It was chloride was a weaker ligand, so it let these stay as unpaired electrons, and allowed it to go for an sp3 hybridization, giving you a tetrahedral structure and unpaired electrons, hence paramagnetic. Whereas nickel here with carbon monoxide with the carbonyl, it gave you nickel here was in zero oxidation state. So it becomes diamagnetic because these two electrons, nickel, the CO is a stronger ligand. So it caused these electrons to pair up, thereby making sp3 hybridization possible, leading to a tetrahedral shape. So tetrahedral shape, sp3 hybridization, but diamagnetic in nature, because here nickel is in zero oxidation state, whereas here nickel with the cyanide, again a strong ligand, but here nickel is in +2 oxidation state. So there's availability, these two unpaired electrons are made to pair up, thereby making it available one more, one d orbital. So it now prefers to go for, instead of a tetrahedral sp3 and a paramagnetic structure, because it is a stronger ligand, it tends to cause the electrons to pair up and thereby making it diamagnetic and for giving you a hybridization of dsp2, which is a square planar and diamagnetic structure. So these are some of the examples of nickel. Similarly, you can have platinum. They give you, whereby in platinum, say in the chloride complex of platinum with chloride, you have the 5dx squared minus y squared. It combines with the 6s, 6px and 6py orbital to give you dsp2 hybridization. So these orbitals then participate in a covalent sigma bonding with the ligands, and the bonding electron, it pairs up using the lone pair of electrons that are furnished by the ligands. So they give you, so most of them you'll have with the ligands such as chloride, nickel forms 4-coordinate paramagnetic and tetrahedral structure. So normally one says that there is uh, a useful rule which originally was called the magnetic criterion of bond types, which allows prediction of the geometry of the 4-coordinate D8 complexes if its magnetic properties are known. Say normally, if it is diamagnetic, that means it will be square planar structure. If it is paramagnetic, that means it would be a tetrahedral structure. So if you know the magnetic property of a D8 coordinated complex, then you can say it's easy to predict. You will do it also, you can do it, but in a jiffy you can say that diamagnetic means square planar, paramagnetic means tetrahedral. And we saw the examples. We have done that. Nickel, this with cyanide was diamagnetic, so that means it is square planar. If it was tetrahedral, then it means it is in the D8 ion state. If it will give you a tetrahedral structure. So now some exceptions will be there, but not, depending on the type of ligand that is attached. So the valency bond picture for 6-coordinate octahedral complexes we have already seen, and so that uh, you can work out many more examples. Try to work examples related to these and see what they are, and you'll get a hang of how to do them. You must remember, for that you must know the periodic sequence of how the metals are placed, so that you know the outer electronic configuration should be known to you. And apart from that, there was one more thing. The failures of valency bond theory. What the successors were, that with the simple method of these box diagrams, they could explain knowing the magnetic behavior, you were able to explain the structure. So the one could explain the magnetic behavior, why one was magnetic, why the other was diamagnetic in nature, paramagnetic or diamagnetic in nature. That could be explained using this simple theory, and calculation of the magnetic behavior could be done using this root over n plus 2. So depending upon how many unpaired electrons are there, you can find what is the magnetic property of it. So what will be the magnetic moment of that in terms of Bohr magnetone. So this is there. Now the
Ma'am,
failures, huh?
one question.
Yes.
Ma'am, magnetic moment based on VBT or VBT based on magnetic moment?
VBT
Which
based on
comes
magnetic moment, VBT based on magnetic moment, because we experimentally they could determine the magnetic property. It was possible to determine. So based upon their magnetic property, he was able to hypothesize. It's a hypothesis. He was able to hypothesize and give that yes, this is the magnetic property of this. It is a paramagnetic or diamagnetic. Then he said that, oh, this is possible. At that time, they did not know whether the ligands are strong or weak. The so-called spectrochemical series were really not known to them. He did not know why they were. He knew that this ligand is strong, so it is pulling, causing it to go. But why is it strong? That valid explanation he did not have. The electrochemical series was there. They could measure it, but he did not know why we had that some ligands behave like a strong ligand and some ligands behave like they are behaving like strong ligand, and he could justify that by knowing that magnetic property. If one is diamagnetic, he knew that, oh, it is a strong ligand, it is able to push the electrons, so cause it to pair up. That is why it is diamagnetic in nature. So he could surmise that way. Knowing their magnetic properties, he was able to explain their structure, that yes, if it is paramagnetic in nature, then maybe it is sp3 hybridization. If it is diamagnetic in nature, then it is square planar. And these four coordinated complexes, they are square planar in nature. So the hypothesis could be given based upon these.
okay, ma'am.
Then there is what are the failures of VBT? Okay, let me open this. So valency bond approach, we have already seen the limitations of valency bond. It involves a number of assumptions. They have assumed a number of things because they didn't know at that time what was the reason for a number of the behavior that was there. But because this was paramagnetic, so it has to be this. Because this is diamagnetic, so it has to be this. It does not give quantitative interpretation of the magnetic data. It does not explain the color exhibited by coordination. The compounds are very colorful. So color, we know that color, a compound appears colored because it absorbs a certain radiations in the visible range. So it absorbs based upon the Webb-Gure. So what it absorbs, suppose it absorbs in the violet range, if it is absorbing that, so the color that is being reflected, the complementary color, the complex will look like that. So here he could not understand why, how it was happening, because here the d orbitals that we are talking about, we are assuming that they are all at the same energy level. So only when there is a jump, absorption of energy is there, then only there will be a reflection, a release of energy. So that conceptualization was not there. He could not understand why there were some complexes which were, and they were varied colored complexes. That explanation he could not give. So why they were, he could not give a quantitative interpretation of the thermodynamic or kinetic stability of the coordination compounds. It does not make exact prediction regarding the tetrahedral or square planar structure of the four coordinated complexes. It does not distinguish between weak and strong ligands. There's no basis just because it was a paramagnetic, so as he assumed that this was a weak ligand. Just because the complex was diamagnetic, so assumed that it was a strong ligand, CO was a strong ligand, but there was no basis for him to distinguish between a strong and a weak ligand. And in order to explain his concept, he also gave another interesting thing that he talked about. Where were we? Uh, he was talking, he talked about a few things. That is, so this is the common, just for your understanding, the simpler ones we have put it here. Order of strength of ligands with donor atoms. Those contain the carbonyls, CO, nitrogen, oxygen, halides. Halides are the weaker ones. Then comes those containing the oxo ligands, this containing the nitrogen ligand, the amines, etc., that you have, the nitrites, the nitrates, the carbonyls. So this would be the just as a clue for you to understand. Of course, we will understand that as we move to the higher theories that we come to. But for VBT, this is enough, and this was given as experimentally. It was determined that the series of ligands, they were arranged in decreasing order of their strength. In determining experimentally, he could determine and get the spectrochemical series, that the carbonyls, the nitrites, the amines, the carbonyls, then amines, then nitrites, nitrates, then the oxo ligands, the OH ligand, then the aqua ligand, and then comes the aqua ligand would be in between somewhere. Then you would have all the halides being there. So that would be the range of these. And in order to explain this concept of hybridization, because this is an issue with all the compounds or the complexes, that we are talking about a process wherein the central metal atom, which is, let us say, either a central metal atom or a central metal cation, which is in a positively charged ion, the ligands are having are more electronegative in nature. They have lone pair of electrons. They are the Lewis bases, which are interacting with the Lewis acid, so with the central metal atom, which is acting as the Lewis acid, and they are combining together. The ligand is sharing its electron with the central metal atom. So say a metal atom with +2 oxidation state, that is sharing, and the ligand brings a 6 lone pair of electrons. So now the metal atom, it just needed 2 of them. So what is happening? But it is getting 6 of them. That with 2, that means 12. So that is a highly electronegative. That would make it unstable. But that is not happening. What is happening is that the metal complex that is formed is stable. That is why it is remaining as a metal complex. And we have a variety of such stable complexes. Although 6 of these charges are coming towards it, the lone pair of electrons are coming and reacting with it when it has asked just for, say, +2 state. So it needed just 2 of those. Then how does it stay stable? Then he explained it, Pauli's exclusion principle. Sorry, we call it as the Pauli's electroneutrality principle. The Pauli's electroneutrality principle explains it in the way that it says that these ligands are electronegative, containing highly electronegative ions, and as a result, they do not give totally the lone pair of electron to the central metal atom. They say that we are sharing it, but the sharing is just enough for the metal ion to become electrically neutral. Most of the time, the electrons are staying with the ligand itself, with the nitrogen or the oxygen, or the fluoride, whichever it is staying with the ligand itself and giving just enough of its that negative character, so that the metal remains electrically neutral and satisfying its electropositive charge and making it electrically neutral. That is what is termed as Pauli's electroneutrality principle. Okay, and tomorrow in the next class we will discuss about the crystal field theory. Today I'll upload these in your system. Okay, then you can leave.
Can you mark me
Thank
present?
you, ma'am.
Thank you.
Yes, dear.
Thank you,
Who's
ma'am.
that?
Thank you, ma'am.
Gaurav Kumar.
Thank you, ma'am.
Who's
Thank you,
that?
ma'am.
Gaurav Kumar.
Gaurav, were you not LinkedIn when I downloaded the attendance?
Ma'am, I joined late. After that, I joined.
How late?
10:22 around.
Oh dear.
Sorry.
Okay. But please try to be there within 10. I try to start my class after 10 minutes. But if you don't be beyond that, please don't do that. 10
Yes.
o'clock is not very early. You all should be there by 10, right?
Yes, ma'am.
Okay.
Ma'am,
Bye.
can we leave?
Thank you.
Okay.
Sure. Please
Thank
leave.
you, ma'am.
Mm.
Thank you, ma'am.
Okay.